Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the mean or expected value. The goal is to define the mean mathematically and to discuss its limitations. The prerequisites for this material are discrete and continuous random variables. Alright, so imagine we have a data set where each data point can take one of a discrete set of values, and then we compute the average. This is a very reasonable way to compute a typical value in the data set. So what do? We add all of these numbers and we divide by the number of data points. Okay? So now the question we're going to ask is, what if I want to consider what the average of a random variable is? Okay, so let's see. What do we mean by that? What we mean is, what if the data were generated by a random variable A? What would be its average in the limit where we would have an arbitrary number of data points? Well, if you think about it, when we're adding up these numbers, essentially we can consider how many times we count each of them, right? So imagine here that the random variable can only have values 3 and 4, let's say. So then we can consider, okay, how many times do we add the number 3? Well, it's the number of data points equal to 3, and then we divide by n. How many times do we add the number 4? The number of data points equal to 4, and then we divide by n. But now when we write this like that, we realize that here what we have is the fraction of data points equal to 3 or equal to 4 divided by the total number of data points. When n is really large, we already explained that this intuitively, this fraction of times that a particular value appears, should correspond to the probability of that value. So here what we really have is a weighted sum of all the possible values times their probabilities. That's what an average is if the data are generated by a random variable. So there are examples from a random variable. And we take this limit where the number of data points goes to infinity, and we assume that the fraction of times every point appears is equal to its probability, which is how we defined probability to begin with. Okay, so intuitively, the expected value or the mean of a random variable can be defined quite reasonably as this sum of all the possible values weighted by their probabilities, which is the value of the PMF of the random variable at that point. Okay, and that's exactly how we define the mean, first moment, or expected value of a discrete random variable, as a sum over all its possible values of those values weighted by the corresponding probabilities. If that sum converges, then we say that that's the mean of the random variable. Let's do an example. You might remember this example from our lecture on discrete random variables. There we had this distribution of the goal difference in a soccer game between Barcelona and Atletico de Madrid. We said the probability that the goal difference is -2 is 0.1, the probability that the goal difference is -1 is 0.2, and so on and so forth. So now let's imagine that we want to compute the mean of the goal difference, okay, which we denote by that. This E, by the way, just refers to the fact that this is the expected value, okay? Because we also call the mean the expected value of the random variable. Okay, so now what are we going to do? We're going to sum over all the possible values that go from -2 to 2. We multiply the corresponding value by its probability. So we're going to take -2 multiplied by 0.1, -1 multiplied by 0.2, 0 multiplied by 0.3, 1 by 0.25, 2 by 0.1, and 3 by 0.05. And we're going to add up all those values. This is exactly what I just said, if I don't make any stupid mistake, which I often do. And then boom, the average or the mean, okay, the mean or expected goal difference is 0.2 in this case. Okay, so what if we're interested in a function of the data or of a random variable as opposed to just the value of the random variable itself? So imagine that again we have this data and we're interested in a function of the data, for example, the square. A reasonable way of finding a typical value of this function, of the square of our data, for example, is just to take the square, or whatever function we're interested in, and averaging it. If we do that, we can follow exactly the same argument as before. We can say, okay, so we have this sum where how many times are we counting h of 3, for example? Well, the number of times that we observe a 3 divided by the number of data points. And this, again, when we consider many data points, just approximates the probability, tends to the probability of 3. So again, we have a weighted sum, except that now where the value that we're multiplying by the probability is this function that we're interested in. Why is this interesting? Well, we'll see in a moment. Actually, I was getting a little bit ahead of myself. So first, let's say that this is how we're going to define the mean or expected value of the function of a discrete random variable. But why is this interesting? Because you could always just, say, okay, like this is a random variable itself. Why don't I just compute the PMF of this random variable and I apply our original definition of mean or expected value? Well, this is usually much more complicated. You have to find the whole distribution of this new random variable, whereas here, if you already have the distribution of A, then you don't need to go and compute the whole distribution of HA if you only care about the mean or expected value of HA. And this is very useful in many cases. Let's do an example. In the case of the goal difference, you might be interested actually in how many points the team, a certain team, so the team that we're interested in, is going to gain from this game. So if they lose, they're going to earn 0 points. If they tie, they're going to earn 1 point. And if they win, they're going to earn 3 points. Okay? So if the goal difference is below 0, we have this random variable x that is going to be equal to 0. If the goal difference is 0, then the random variable x is going to be equal to 1. And if the goal difference is above 0, then x is going to be 3. So we could, in principle, compute the PMF of x, and we did this in the lecture on discrete random variables. But if we only care about the mean value or the expected value of the points x, we can actually do this directly. So what we can do is we can say, okay, the mean value of x is the mean value of h of g. And now we can just take this weighted sum of h of g, where we plug hg here, and this is the important part, we just need to use the probability of g. So what are we going to do? We're going to say, okay, for this value of g, x is equal to 0. So we're going to do 0 times the probability of minus 2, which is 0.1. 0 times, because minus 1 also corresponds to 0, times the probability of minus 1, which is 0.2. Then we're going to be like, okay, 0 corresponds to 1. So we're going to do 1 times the probability of the goals being equal to 0. So 1 times 0.3, and then 3 times this, 3 times this, and 3 times this, because all of these guys correspond to x equals to 3. And that's very nice, because then we didn't have to derive the whole distribution of the points to just compute their mean value. We could do it directly with the distribution of g. And this is often very, very useful. And it turns out that the mean number of points earned by the team is going to be 1.5. I forget if the team of interest was Barcelona or Atlético de Madrid. I don't remember. Okay, so what if you have multiple random variables? This often happens in probabilistic models. We have several random variables. Here we're observing pairs of two different quantities. Okay, so here we have this data, two different quantities that are going to be represented by random variables a little bit later on, and we're interested in a function of the data. Okay, some function that maps these two numbers to a single number, and we want to know the average of that single number. Well, the average of that single number, we can just look at the different examples and just add them up and divide by the number of examples. So we're going to follow exactly the same argument that we did previously, and we're going to say, okay, how many times are we going to take into account a particular combination, like maybe 3 and 4, h of 3 and 4? Well, it's going to be the number of times that we see 3 and 4 together, that particular pair together, divided by n. And what is that? Well, that's when n goes to infinity. That's exactly how we defined, or how we think intuitively, of the probability, the joint probability of x and y. So this sum is going to be whatever value we're interested in of a and b, weighted by the joint PMF of a and b. And that's how we define the expected value or the mean of a function of two random variables. Okay, we sum all the possible values of this function weighted by the corresponding values of the joint PMF. Again, let's look at an example. Actually, I jumped a little bit ahead. If we have a random vector, so instead of just two random variables, we have 20 or however many, we do exactly the same thing. We multiply whatever function. So realize that here we're talking about functions that map these 20 entries of the random vector to a single number, because we need an average, right? Like we're interested in a particular quantity. Later on, we will look at generalizations of a mean of, a mean in several dimensions. Right now, we're talking about the mean of a single number, okay, of a one-dimensional number. So this function h of x maps the random vector to a single number. If we want to know the mean of that single number, what we're going to do is we're going to add up h of x over all the possible values of x and weight them by the value of the joint PMF at those values. The value at those values. Okay, this is not, maybe not my best explanation, but let's move on. Okay, so now let's do an example. The two random variables that we're going to be interested in here are c, which is the number of cats that people, let's say around Washington Square Park, have, and d, the number of dogs. I completely made up this data. If you know of a data set where we have real data like this, I would be interested, because my wife, for example, was claiming that more people have two cats than just one cat. I don't think that's the case, but I would be interested in looking at some data. Anyways, so just to be clear, this is the joint PMF. If you want, for example, the probability that someone has two cats and one dog, that's 0.03. And now we ask ourselves, what is the expected value of the number of pets, of cats and dogs, that people have in this population of people that I just invented? This is just c plus d, so it's a function that maps the two random variables to a single number. For example, it maps 2 and 1 to 3, 1 and 0 to 1, and so on. Okay, so how do we compute the expected value of this function? We look at all its possible values and we sum over the corresponding probabilities. So we're going to say, for example, 0 times 0.35. Then we're going to be like, okay, 1 plus 0 is 1 times 0.15. Then we're going to be like, okay, 2 plus 0 is 2. So 2 times 0.1. Let's do a more interesting one. Maybe 1 and 1 is 2. So we're going to multiply 2 times 0.05. And we're going to add up all of these weighted values. And just going to show you. Okay, so we're going to take all the possible values of c plus d, multiply by the corresponding value of the joint PMF, and boom, this is what we get. The average number of pets in my invented example is equal to 1.05. And again, where do these numbers come from? This 0.303, for example, where does it come from? Well, we took this probability and we multiplied times the corresponding value of c plus d. In this case, 1 plus 2, which is 3. Okay, and we do that for every entry of the joint PMF, essentially. Okay, so now we've talked about discrete quantities up to now. What happens if I have continuous quantities, which I'm often interested in? Let's say that the data now look like this. Okay, so continuous values. Averaging is still a reasonable way to compute a typical value, right? Like we can still, sum all the possible values and divide by the number of data. That's a very reasonable way to estimate a typical value in this data set. So now let's ask again, if these data are generated by a random variable, what should be the mean of that random variable in terms of its distribution? Okay, that's really what we're asking. Okay, so as usual, things with continuous quantities get a little bit messy because we cannot reason with probabilities directly. Usually we want to reason with the density. So we always take limits and so on. It's a little bit annoying. So now imagine that what we do is we say, okay, these numbers can be in the real line, but let me cut up the real line into a grid, okay, which has width epsilon. Okay, and on this grid I do have discrete values, okay, and so on. Okay, where I have like, it goes back, right? So I can have a0, a minus 1. I'm just covering the whole real line with a grid of width epsilon. And now I'm going to look at this average. And I'm going to do kind of roughly the same as I was doing for the discrete values. I'm going to say, how many times do I see, do I have something close to A2? I'm gonna basically map all of these guys to A2, and then all of these guys to A3, and so on. Okay, and then when I collapse epsilon towards A2 or A3, that's going to be very close to the average. So how many times do I map a certain, some values to AM? Well, it's the number of data that end up between AM minus epsilon, for example, A1 or A2 minus epsilon, and that value, right? And now here, I'm dividing by n. So what I have here is the number of data that lie in an interval divided by the total number of data. That's just when n goes to infinity and have a lot of data. That's just the fraction of values that are in that interval, which is equal to the probability. Or at least that's our intuitive notion of what the probability of the random variable being in an interval means. How do I write that probability in terms of densities? Well, it's the density at AM times the width of the interval, okay, times the width of the interval epsilon. So now I have a sum of some quantity times the density times epsilon on a very, very fine grid. If I take the grid to the limit where epsilon is equal to 0, this, by calculus, is just an integral. So what I'm doing, I'm integrating A against the density, and then the epsilon becomes a differential. So essentially I have the integral, where it's often the case. When we have something in the discrete case and we go to the continuous case, the sums become integrals. This happens all the time. In this case, we again have, it's not a weighted sum, it's a weighted integral of our quantity of interest, which is A. And this time it's weighted by the density instead of the PMF, but otherwise it's the same thing. And this is how we define the expected value or the mean of a continuous random variable. Okay, we multiply the possible values of the random variable by the corresponding density, and we integrate over the whole real line. Okay, that's the expected value or the mean of a continuous random variable. Let's do an example. What if we have a uniform random variable in a certain interval AB? We integrate from minus infinity to infinity, but a lot of it is 0, obviously, the PDF times the possible values. In this case, the PDF is 1 over b minus a. Remember that a uniform random variable in the interval from a to b is equal to a constant, like the PDF is equal to a constant, but the PDF has to integrate to 1. So that's why that constant is 1 over b minus a. And now we integrate this. If you remember, the integral of u is u squared divided by 2. So we have b squared minus a squared divided by 2. And now this thing up here is just equal to b minus a times b plus a. You remember your calculus. So we end up with the midpoint between a and b, which is a very reasonable typical point in the distribution. Okay, right in the middle. So here I'm showing you when it's a uniform random variable between 0 and 1, the mean is 0.5, which makes a lot of sense. All right, so what if we have a function of a random variable? I'm not going to repeat all this business with the grid and so on, but it's essentially the same argument. Tells us that now we can actually take the function that we're interested in, let's say the square or whatever, and weight it by the corresponding density. This is nice because we already saw that it's kind of annoying to have a function of a random variable and have to derive the whole density. We often went to the CDF, right? What is the CDF? We derived the CDF and then we took derivatives. It's kind of annoying. So being able to compute the expected value directly is actually very nice. So let's do the example that we already did when we derived the whole density of this voltage across a resistor. And if you remember, it got a little bit complicated, square roots and stuff like that. Here you're going to see that it's much more simple if you just want the expected value. Of course, the expected value does not give you as much information as the whole density. So there's that trade-off. Anyways, so we have a circuit. The voltage V across a certain resistor is uniform in 0, 1. And we want the expected power dissipated in the resistor. You don't know much about circuits. It doesn't matter. What's the whole point? The whole point is that the power is given by the square of the voltage divided by some constant R. So we essentially, what do we want? The mean of the square of a random variable where we know the distribution of the random variable. So we could, in principle, derive the whole distribution. And we know how to do it. You go to the CDF, then you differentiate. It's a little bit annoying, but we know how to do it. But if you just want the mean value or the expected value, it's actually much simpler to apply directly this formula that we just introduced, where we say that the mean is equal to the mean of this function. Actually, I forgot. I should have put a squiggly line on top of the V, right? Because it's a random variable. Let me put it again. This is my punishment for the typo. And now we integrate against the density. So here the density is easy, it's just 1. So we take the value of that function, which is v squared over r, and we multiply by density, which is 1, and we integrate from 0 to 1. Now, the integral is with respect to v. You should always check very carefully what you're integrating with respect to. And the integral of v squared is just v cubed over 3. So we end up with 1 over 3 times r. That's the mean. Much easier than rederiving the whole density. So what if we have multiple continuous random variables? Same thing, except that now we will use the joint density, just like we use the joint PMF. We multiply by the value of that function. Again, we're considering functions that map the two random variables to a single value. And then we just take that integral. For a random vector, same thing. We're considering functions that map the vector to a single value. We always multiply by the joint PDF of the vector, and we integrate over all possible values. Let's do an example. Imagine that you grab an amount of sugar uniformly distributed between 0 and 1. And then you spill an amount that is uniformly distributed between 0 and whatever quantity you grab. And now I ask you, what's the expected amount of spilled sugar? Okay, so let's first model this with random variables and so on, and then we'll see what we need to compute. So first we have an amount of sugar uniformly distributed between 0 and 1. That's going to be easy. And then we have the spilled amount of sugar, which is uniformly distributed between 0 and however much sugar we grabbed. So we already see that this is going to be some conditional distribution, right? Start thinking about how you would model this. Okay, so what's the distribution of the sugar that you grab? Again, I encourage you to stop the video and think a little bit about it. This one's easy, it's just uniform in 0, 1. Now, how would you characterize the distribution of the sugar that you spill? So again, however much you got, now you're going to spill something uniform between 0 and however much you got. Well, it has to be conditional, right? Like it's conditioned on having grabbed G, you're uniform between 0 and G, right? So we have the conditional PDF of S given G. And now we want to compute the mean of S. So we could actually just compute the PDF of S. How would we do it? Well, we have the marginal of G, we have the conditional of S given G, we can build the joint PDF through the chain rule and integrate, and that's going to give us the marginal, and then we could compute the mean. Or we could just think of S as a function of S and G, right? It is a function of S and G. A bit of a dumb function, but it is a function, right? So you can say, oh, this is a function of S and G, so let's apply the formula. I multiply the value of that function times the value of the joint density, and then I integrate over everything. You might be like, oh, so why don't we just put the density of S there? So let me ask you that question. Why don't we do it? We don't because we don't know it. We would have to actually kind of do this, put the marginal and the conditional, and then integrate over G to get the density of S, and then we would plug it in. Because of that, we're not going to. We're just going to use the joint here. And for the joint, we're going, because that's what we know, we're going to plug the marginal and the conditional, as I just said. I got a bit lost there for a moment. Sorry. Okay, now I'm back. So what is the marginal here? The marginal here, this one, is just uniform between 0 and 1. And then this one is uniform between 0 and G. So what is the density? A density that is uniform between 0 and G. What's its actual value? It's 1 over G. So here, that's where this 1 over G comes from. And then this guy is just equal to 1. So we end up with an integral that goes from 0 to G, right? Because S is uniform between 0 and G, if we condition on G. And that's also where this density comes from. And we're multiplying times S because we want the mean of S. That's what we want. And like at the end, we need to integrate G from 0 to 1. The density with respect to G is just equal to 1. So I didn't even write it. Okay, so now we take this integral. First, and this is the tricky part, we have to realize that we have to integrate with respect to S. So if we integrate this thing with respect to S, we get S squared over 2 from 0 to G. So we get G squared over 2. G squared over 2 divided by G is just G over 2. Now we have to integrate this with respect to G. So this is going to be G squared over 2 between 0 and 1 is just going to be equal to 1/2. So we end up with 1/4. I strongly recommend that you try to reproduce this on your own and see if it makes sense to you. Okay, so what if we have a mixture of discrete and continuous quantities, which often happens in probabilistic modeling? Then by the same arguments we were using before, essentially what is going to happen is, if we're interested in a function of these two random variables, C and D, we're going to take that function and we're going to weight it by this proxy of the joint distribution that we had, where we take the marginal with respect to the continuous random variable, the marginal PDF, times the conditional PMF of the discrete random variable, or the other way around. Both of these things are exactly the same by the chain rule for continuous and discrete random variables. And then we integrate and sum over all the possible values. Okay, and again, it's by exactly the same argument that we use with the discrete and continuous random variables. It's important to realize that we need to use the conditional here. Okay, this has to be a conditional, one of them, because you want to take into account the joint distribution of the discrete and the continuous random variable. Let's look at an example. We're going to go back to one of the examples that we used with discrete and continuous random variables, where we flipped a coin, but we didn't know what the probability of heads was. So we assumed that the probability of heads, which was theta, was uniform in 0, 1. And now, under that prior assumption, what is the mean of the coin flip? So we're going to again use this trick where we say, well, the mean of the coin flip, which we're going to call A, okay, let's call that A, is a function of A and theta. It's a little bit of a trick to use directly the joint of both, because again, we know how to do this, right? We could compute the marginal of A and then just compute the mean of A from the marginal. But if we want the mean, just the mean, why go in these two steps? We can apply this directly as long as we use the joint distribution here. Okay, so now we plug these things in. Here we have to sum over 0 and 1, but when we sum over 0, when we put a 0 here, the whole thing is just going to be 0. So we're going to end up with just the value for which A is equal to 1. Okay, that's the term that that is not going to be equal to 0. For that term, this is just the probability that A is equal to 1 given theta, that's just equal to theta, okay? And this guy is uniform between 0 and 1. So we end up with, actually I made a mistake here. There should be a theta there. This is going to be our little secret because I don't want to re-record this because I still have to record a couple of videos after this. Okay, so theta integrated between 0 and 1 is going to be theta squared over 2 equal to 1/2. Okay, and the point is that we use this trick of saying this is actually a function of theta and a, so I can just plug in the marginal and the conditional there and sum over all possible values of the discrete random variable, in this case 0 and 1, and only 1 produced a non-zero value, and then I have to integrate over all the possible values of the conditional. If I knew the marginal and conditional in the opposite direction, then I would first integrate and then sum. All right, I hope that makes sense. Okay, so let's look at some real data. It's always good to look at some real data. These are NBA salaries in the 2017-2018 season. And I computed the mean, and I'm showing you the histogram of variables. So you might notice that it seems like a lot of players are here and very few players are here. So we could ask, for example, how many players earn more than the mean? And naively, you might be like, well, if it's kind of a typical value, I would expect like half of them will earn more than the mean and half of them will earn less than the mean. Okay, so how many NBA players earn more than the mean? The mean is almost $6 million. Kind of nice being an NBA player, I guess. Less than 1/3 of the players earn more than $5.8 million. And around 70% earn less. So it seems that the mean is skewed towards large values, which is weird, right? Because we think of it as a typical value. So what is happening? Why is this happening? In order to understand why this is happening, we're going to look at a simplified example where we have a random variable that has some extreme values here. Okay, so most of the density of the random variable is here between minus 4.5 and 4.5, but there's a little bit of the density here between x minus 0.5 and x plus 0.5. Okay, and the important part to realize is that this is centered around 0. And then we have a very small part, like with small probability, you get a really, really large value. So with very small probability, you're LeBron James. Okay, so you earn a lot of money, but mostly you're not LeBron James. Mostly, I don't know, you're like a bench player for the Charlotte Hornets. Okay, so, or, you know, I'm not laughing at them, obviously. You know, it would be really nice to be a bench player for the Charlotte Hornets. Okay, so now we're going to compute the mean of this random variable and see what happens. So we have to integrate a from minus 4.5 to 4.5. Oh, and sorry, something that I said is, I forgot to say is that the density is uniform. How do we know what the density would be? Well, you need to see how big this interval is. This interval has length 9, and this interval has length 1. So the density is going to have to be 1 over 10 so that it actually integrates to 1, because you know the area under this has to integrate to 1. I forgot to say that. Okay, so now we're going to integrate this from minus 4.5 to 4.5, and then from x minus 0.5 to x plus 0.5. So we plug that in. This 1 over 10 comes from what I just told you about the density. Now we realize that here we're integrating an odd function from minus 4.5 to 4.5. Okay, so maybe I'll show you in the picture. It's like an odd function, so it's going to cancel out. You can check, you can actually go through the math, but it's essentially going to cancel out. You're going to get 4.5 minus 4.5, it's going to cancel out, okay? 4.5 minus 4.5, sorry. Like it's going to cancel out because this is an odd function, so this is going to be 0. And now we just get the integral of this, which is going to be a squared over 2 from x plus 0.5 to x minus 0.5. Okay, so we get this formula. When we expand this, the squares cancel out, and we end up with the cross terms. The mean of this random variable is x over 10. And this is kind of problematic, right? Because there's a very small part of the probability that is here, and if I take x to 1 billion, the mean is 1 billion over 10, right? So this small fraction of the values that have non-zero probability completely distort the mean. They completely govern the mean. If I make them ridiculously large, the mean becomes ridiculously large. These guys basically don't matter. So that's kind of problematic when you have situations like the NBA players where there's a few players making an immense amount of money and most of them don't make that much money. And this happens in many other situations too. This is not just special to NBA salaries. Here we see the mean. Actually, we see how the mean is at x over 10. In this case, x is equal to 100. Again, if I took this guy and I took it to 1 billion, then the mean would move with it. And that's not very satisfying. So for this type of data, if you want a typical value, you probably don't want to use the mean. Essentially, that's the take home. So what should you use? Well, we can go back to our original argument where we were saying, well, like in a typical value, about half of them should earn less, half of them should earn more. What does that remind you of? It should remind you of the median, because the median is exactly that. It's a number m such that the probability that you're below m is exactly 1/2. Okay, and the probability that you're above m obviously is also 1/2. So we can think of, let's compute the median for our example, and let's see how it depends on these extreme values. So again, we're uniform between minus 4.5 and 4.5, and x minus 0.5 and x plus 0.5. So we can compute the probability until an arbitrary number m. Okay, this is going to be 1 over 10. So if we stay within minus 4.5 and 4.5, that's just going to be m plus 4.5 divided by 10. And if we set this equal to 1/2, what we get is that the median is actually at 0.5, which is between minus 4.5 and 4.5. So we're good. This is a reasonable way of, this is a correct calculation. And this is very nice, because if you realize, what is the dependence with x? There's no dependence with x. If I come here, the median is going to stay there at 0.5 no matter where I send these guys. I can send them to 300 billion. I can have a player that earns $1,000 million. It doesn't matter. The median is going to stay where it is because there's always half of the players that are here, no matter how rich the richer players get. So in this case, for this kind of data sets where you have very extreme values, the median is a much more reasonable way of estimating a typical value than the mean. And indeed, the median salary for the NBA players is 2.39 million, which is, significantly, it's less than half than the mean, which is 5.86 million. Okay, so that's the take home here. The mean has this limitation. It can be extremely distorted by extreme values. Okay, so what have we learned? We have learned the mathematical definition of the mean, and we have learned an important limitation, which is that it can be very distorted by extreme values. Thank you very much.